In this next series of lectures, we're going to look at the different genres of artificial intelligence. And what I really want to do is try to walk you through where it came from, how it works, and where we're currently at with each of these different genres of AI. And I'm going to flag right now that many of these are interchangeable. There's a lot of overlap, but I'm creating a little bit of an artificial boundary between each of these five pieces because what I think it allows for us to do is really sit down and think about how this specific genre works and the implications for design as we move through the stack and start to actually integrate many of these different types of technologies. Let's begin by thinking a little bit about cybernetics, or robotics, as we call it in the modern day. We have been designing automata of different kinds for a very long time. And I say this over and over. But the reality is that when you think about what an automaton is, it is a automation of mechanical action, right? So whether it's this elephant clock in which they were imagining how something might move through the system, or Leonardo da Vinci's Mechanical Knight in 1495, where he was thinking about simple automation of hand action, or even this karakuri puppet that serves tea. This was an ancient Japanese mechanism that was mostly used to provide delight. But as we sort of began to build more and more different kinds of automata, the level of sophistication started to increase, right? If we think back to the technological changes that were happening during this time, there were so many different ingredients being introduced, whether it was different kinds of materials, different kinds of understanding, that were able to actually start to begin to get more and more sophisticated. So much so that sometimes we would even build things like this. This is the Mechanical Turk in 1770. This was a chess-playing pseudo-automaton. And for the longest time, people thought that we had actually developed a chess-playing automaton. People would come and play chess with it and would be, foiled by this machine. But the reality was, under the hood was a guy just sitting there playing chess back. It was still an ingenious device. It was still filled with intricate mechanisms, but it was mostly trickery, which is an interesting juxtaposition because from this Arthur C. Clarke quote that talks about this idea of technology, right? So any sufficiently advanced technology is indistinguishable from magic. And oftentimes when we look at different kinds of tools, especially modern day AI tools, they sometimes feel magical. But I want you to remember that under the hood is human effort, and under the hood are different kinds of constructs that we have actually put together. So in 1948, Norbert Wiener introduced the concept of cybernetics. He wrote this incredible book called Cybernetics, or Control and Communication in the Animal and Machine. And, he was a polymath. So this spanned so many different concepts and disciplines. At its core, you can define cybernetics as the study of controlling the flow of information in systems with feedback loops. Now, he had many applications outside of computing, but I'm going to really just focus on the applications within computing for our conversation today. Here you can see these four concepts that actually came from his book. But again, we won't go through each of these in a lot of detail because they start to sort of intermingle as we move through time. But the four concepts were, right, this idea of feedback and control systems that led to advances in robotics. A lot of his work was actually in signal processing, and we'll talk about that when we get to logic later on. He also had a lot of really interesting ideas around different kinds of animal-machine analogs, and was one of the first folks to really talk about the idea of artificial neural networks. Right, but at the core of it all, he was really a systems thinker. And so he also talked about ideas like symbiotic and self-organizing systems, drawing from biology, thinking in terms of biomimicry, to really think about the implications for design across the informatics disciplines. Someone wrote a kid's book at the time trying to explain cybernetics to others. And I love this image, right? It talks about how an alarm actually rings, right? In this particular case, it allows us to sort of start thinking about ideas like explainability of how things work. And it allows us to think about how we can communicate the ways in which things work to each other, to be able to not necessarily think about these, right, esoteric ideas around machines that we can't understand, but really try to think about how we conceptualize machines which seem to think. Right. Wiener was very popular because of this book, but a lot of his work really sort of, right, focused in on this idea of being able to mimic the human brain. Right. So by copying the human brain, he sort of helped us think a little bit more about how to build better calculating machines. And now it's important for us to not necessarily also be limited by this idea of just trying to mimic humans, as we've talked about before, but really just trying to think about how can we be inspired by looking at ourselves as we think about the design of technology. At the core of cybernetics is the idea of a control system. You can think about it as a system in which there are these two states, the initial state where we are right now, and a goal state where we'd like to get. And the whole purpose of a control system is to move us from that initial state via a process to the goal state. Easy peasy. So you can really think about this in terms of there being a manual input and a direct influence and an output. This is also known as an open loop. For example, a temperature control system that uses an open loop would simply have a push button to increase the temperature, a signal would be sent up to the heating element to increase the temperature, and whoop, the temperature goes up. Great, easy peasy. But what if you want things to adjust? What if you want the world to be adapting to your needs? Wiener introduced the concept of feedback in control systems. And this was revolutionary at the time, right? It meant that you could actually take the output of that second state and use it to influence the entire action all over again. You could close the loop, so to speak. A closed loop system, therefore, has this sort of reference signal, this input that you start with. There's an error detector that looks at this sort of diff, this comparison between your feedback and that reference signal. And then it moves through the system to give you a particular kind of output. And if there is some sort of difference between what you want and where you started, then the desired output is updated, right? An adjustment is made. Let's look at this with a slightly more grounded example. Let's go back to that temperature control system. In this particular case, right, this is an electrical diagram. Well, technically it's a block diagram depicting a closed loop temperature control system. So your desired temperature is input. You can see in the bottom right that you can actually put in your reference input into the controller. The computer then compares your desired and actual sense temperature, right? So there's a sensor that's actually looking around going, is it 62 degrees or what is it now? And then the temperature is continuously adjusted. This is how modern thermostats work, right? And so this idea of feedback is incredibly powerful because you don't just have to, you can now actually close that loop and start to make continuous adjustments, monitor, and really make changes in the system as you're working it. This really laid the foundations for the concept of servos, right? These are essentially control systems with a mechanical position output, right? So it meant that your input was actually saying, okay, robot, move there. There's a lot more in between servo mechanism and robots, but, that really laid the foundation for a lot of the ways in which we think about and build robots even today. So let's spend some time conceptualizing automation. Automation can be defined as the use of technology to perform tasks with reduced, sometimes no, human assistance. But that isn't just a binary thing. It's not, yes or no. There are different levels of automation that we can really go through. Basic automation involves simply automating a simple repetitive task, right? You can think of this as a forklift that just picks a box, puts a box, picks a box, puts a box. Cool. From there, we can bump up a level and think about process automation. Now we're thinking about how can we actually automate a complex set of workflows across systems. Modern software engineering actually involves a lot of process automation where we say, okay, I'm going to make a change in the code here. I want it to do that over there. When I then deploy my code to a server, the entire chain of actions should happen, right? You probably use a lot of different kinds of automated processes in your own work, whether it's simply something like setting up a calendar reminder or even just, saying, okay, the moment I invite so-and-so to a meeting, send them a Zoom invite, right? These are just very basic process automation examples. And really our goal is to, again, get to this idea of intelligent automation, right? But if you look at the core of it, it's a concept of automated responses that improve through learning from priors and context. So it's that feedback concept all over again, right? So at the core of a lot of what we talk about is the concept of feedback as well as of contextual awareness. So let's look at now the different genres of AI that take into account these different ideas. First, let's think about automation. Right. So the first industrial robot was a Unimate, and it was designed to automate the, so to speak, dirty and dreary and dangerous jobs that human workers didn't want to do. Remember, someone had to then define what the dirty, dreary, and dangerous jobs were that humans didn't want to do. I chuckled when I saw this marketing image of the same robot serving drinks at a bar. because apparently that was also an example of a dreary job somebody didn't want to do. But if you look under the hood of what a system like that is, it's again a control system, right? This is a robotic control system, not the same one as the Unimate, but if you look at this control system, you see again sensors, actuators, and underneath the hood would be a variety of different closed loop systems that allow for the robotic platform to be able to learn from. Underneath the hood would be a variety of different kinds of control loops that really allow for us to sense, decide, and act. We see this in action in all sorts of modern day settings, right? There are industrial robots manufacturing entire cars in factories. In this particular case, this is the Audi factory assembly line in Hungary. And you can see from start to finish, very many different kinds of automation and coordination and synchrony that has to happen in order for us to go from metal parts to moving car. A lot of these industrial robots, right, I think it's important to remember, are actually fairly specialized, right? So in this particular case, we're looking at the Da Vinci surgery robot, and you can see that it is designed for very, very specific types of human-robot interactions. In this particular case, it aids a surgeon in trying to be able to do specific non-invasive surgery tasks. In that sense, industrial automation is always a specialized task as we map workflows to determine optimal modes of production in very specific contexts. Each of these examples have required someone to have very specific understanding of how humans have performed these tasks in order for us to then determine what do we automate? What constitutes that tedious, dirty job as something worth automating? And later on, we'll even talk about the sort of idea around the impacts of automation on labor or society. But I want you to really keep in mind this idea of task mapping as something that is critical to being able to produce specialized technologies like industrial robots. We're not quite yet at the point where we're having robots making robots, but you can see how that is sort of the general trajectory in which things are moving, for better or worse. And we'll dig into this a little bit more another time. Next, let's look at robotics. Robots, as a general class of AI, however, are general purpose technologies for the most part. We're clearly still experimenting with form and function. But at its core is that same robotic architecture, right? There's a sense, a decide, and an act for it. In this particular case, we're looking at a slightly more rudimentary sense, act, decide architecture where sensor input data is fed into a decision tree, and that determines actuator function, for instance. If we introduce that concept of feedback in, again, we have this reactive sense, decide, act architecture. But in this particular case, we're introducing concepts around reasoning and monitoring and adaptation as part of that decision-making process, right? So feedback instantiates as reason about behavior of objects, plan to change the world, monitor changes, avoid objects, right? Do something different. And really, one of the biggest things that we started to have to do was think in modules, right? As our robotic systems got more and more complex, it wasn't just a single arm grabbing a drink. We needed to think about how to integrate modularity as an architectural pattern in the construction of robots. And so it means that each of those components might actually become different subcomponents. And so now we're moving from sort of traditional software engineering of a single component to really, right, modular component-based software engineering as we're thinking about the design of these kinds of systems. So let's look at some examples of robots. One of the earliest examples, at least I came across, was the Aibo pet robot dog, which unfortunately one is describing as much less demanding than servant robots. But the Aibo was really meant to provide companionship, right? The goal of this robot was not necessarily to perform specific tasks, although I hear it can jump and pretend to pee and will respond well to pets, right? But really, it's a general purpose technology, right? It's meant mostly for fun and curiosity and maybe even just a little bit of delight. But if we look at that same form factor, Boston Dynamics has gone in a completely different direction with the four-legged robot, right? In this particular case, we're looking at Spot as he performs inspections and site monitoring services using a suite of complex sensors of spatial mapping to then be able to do things like detect when there's an issue or be able to determine what comes next. So robotics have really taken a very wide variety of form factors now. There's some work that looks at the design of exoskeletons. This is actually the Aptronics load-bearing exoskeleton prototype that involves a wearable robotic system. And you can see how there's sort of like, applications and everything from mining and engineering tasks all the way through to like space exploration. I think it's a little bit amusing because in some ways we're already starting to touch on this concept of cyborgs, where robots are really there to augment humans. A different form of augmentation, which I think is equally interesting, is Double Robotics' virtual co-location robot that is designed to support human telepresence. And so in this era of remote and hybrid work, it means you should theoretically be able to log into this little platform over there and then drive yourself around as you interact with coworkers and go about a normal workday. So in this particular case, you could actually see this idea of us using robotics to be able to actually collaborate with each other and augment our own experiences in the real world. We've also used robots to explore space a little bit more experimentally, perhaps. I know that there's examples that are much more grandiose, like the robotic arms on the International Space Station. But here's an example of one that is actually an autonomous robot. In this particular case, the Astro B robots are performing different kinds of maneuvers and some experiments on the International Space Station as we try to sort of think about what role different kinds of robots can play in our work, both here on Earth as well as in space. Right, so we've built a whole bunch of different kinds of robots. A lot of them are fun, a lot of them are interesting, a lot of them are still conceptual things, but we're beginning to see the different ways in which robots can actually start to integrate in our daily life. One of the clearest examples of this is actually in the subdiscipline of autonomous vehicles. So if we go back to this idea of sense, decide, and act, right, an autonomous vehicle would theoretically be able to just go straight. And the moment it sees an issue, it should be able to either steer right, steer left, right, adjust its movement as it's going down a path. We've done this in many different kinds of contexts. One of my favorite examples is Kyla Laird's home tractor hacking experiments, where he'll actually stick together a bunch of microcomputers, and in this particular case, build himself a self-driving tractor that is planting corn. We've seen much more complicated examples of autonomous vehicles. In this particular case, Enduro has developed an autonomous air vehicle, and you're seeing a war game style demonstration in which it can sense, decide, and act. And again, we continue to use our different kinds of robots to explore space and beyond. So in this particular case, we're looking at NASA's Viper rover that is scheduled for launch to the moon in late 2024, right? But at the core, a lot of them are using the same common concepts. Let's take a moment to briefly review the idea of levels of driving automation. In this particular case, there are 5 levels. This is the current standard. And so even though you might see other variations of the theme, this is the sort of automotive engineer accepted definition of the levels of driving automation. A lot of the things that we see today are about a level 1 or a level 2, right? So if you look all the way down to example features at the bottom, right, it includes things like lane centering and adaptive cruise control. And maybe there's a little bit of, gentle support for steering and braking and so on and so forth. So even, let's say, something like a Tesla would be a level 2 autonomous vehicle. Our reach goals are, right, levels 3 to 5. And we don't really see this in autonomous vehicles right now. And we'll sort of talk a little bit about what makes that really difficult and what makes that really complicated. But these are this is one way in which you can start to think about the way in which we start to incrementally increase levels of autonomy when we're building different kinds of AI systems. So there are analogs for this in non-vehicular examples as well. They're just not, standards yet. So the core concept underneath an autonomous vehicle is this idea of the operational design domain, right? So if I have a vehicle, can I detect the environment, geography, time of day, traffic, objects, even people, to be able to say, okay, here's where I'm working within, right? And then that is really what is used to really drive decision-making in the vehicle itself. And so ideally, we would be using vehicle data itself to map that ODD, right? So you'd use sensors to be able to say, okay, here's the region of interest that I'm in. I want to map some initial boundaries. I would use some data and scenarios previously codified, and then I would run these tests or simulations in a closed course before deploying it to the field. And part of the reason why we want to be able to do this is because there are actually some very tricky and complicated questions that we run into. If you see a dog on the road, should you stop? Should the car stop in order to then go hit a person? A lot of people talk about this in the context of the trolley problem. I'm not going to go down that rabbit hole. Instead, let's just keep it really simple and think about even just like basic decisions, right? Should I overtake somebody? Should I speed up? Should I slow down? If there are two drivers in the car, who should I listen to, right? There's some very, very basic things that we have to struggle with before we even worry about, right? Those larger philosophical challenges that even we as humans struggle. The way in which we are bringing in different kinds of data is through a variety of different sensors, right? These are the ears, eyes, and nose of the car itself. It includes, right, a global positioning system, good old-fashioned GPS to know where it is. We are using things like LiDAR and cameras and radar to be able to then see the world around us, right? And then at its core, there's also a pre-built data set. In this particular case, we're looking at, the example shows that it has pre-built maps, right? And every single company, every single researcher is doing this slightly differently. But you can roughly think of this as a generic schematic of an autonomous car, right? It's a system of systems, and people can then specialize in each of those subsystems, right? So modularity writ large, right? So in this particular case, if we look at Waymo's example, right? And Waymo is sort of pushing levels 3 and 4, depending on who you talk to and how much you know about what they're doing, right? But they use a combination of LiDAR, of some, just they have like 29 cameras as well as then radar to then be able to create, right, that spatial map, right, that operational domain around the car itself to then be able to decide what to do next. So if we think about that decision-making process, right, it's not just sensing the world around us. It's really an act of perception, reasoning, evaluation, decision, and then action. It's no longer as simple as just sense, decide, and act. Decide has become a very large and complex system of things. And so if we look at this if we look at this diagram, it sort of walks us through what it would take to actually identify that operational design domain. And you can see that a little bit on the data generator side of this schematic, and then use that to inform your evaluation, like what is the risk level? Am I actually okay with this? Am I okay driving in the snow? And so on and so forth, and then actually make the decision about whether or not the car will move forward. Right. And I say I, but really it's the car's decision-making processes that would have to run through these, right? So you can see the number of different things that we would actually have to codify, right? The number of things that we would have to agree upon before we would allow a tool, a piece of technology to make these decisions with autonomy or on their own. Whenever I think about robots and even autonomous vehicles, I think about the paper, What Is It Like to Be a Bat by Thomas Nagel. He describes this notion that bats have experience and that there is something that it is like to be a bat, right? The bats have different kinds of sensors. They're interacting with the world around them. Their brains then process this information and they use that to make a decision about what to do and where to go. But I don't have sonar. It is a form of perception, but I don't have it. And so I might not necessarily understand intuitively what it's like to be a bat. I might not have that subjective experience, and it might not be within my imagination. This then makes it really hard for me to actually conceptualize what it is like to be a bat, let alone codify a robotic bat, or even, if we go back to where we started, to codify what it means to be human. And so there are a lot of limits to perception, and a big part of moving forward in robotics is, again, not to necessarily get hung up on the philosophical concepts, but to really think about how they can inform what we do when we are designing different kinds of systems. I want to close with a little bit of a discussion around, right, then what does it mean to actually create artificial bodies? I love this infographic by Fritz Kahn, and he takes the human body and breaks it down as a series of industrial systems, right? This infographic, this book was literally called Man as Industrial Palace. And if you zoom in, you can kind of see him taking very literally the human and representing it through a series of manufacturing processes and so on and so forth. In a lot of ways, some of our biomimicry has been doing a little bit of this, right? We've been taking this very squishy concept that is the human or even the mind, and then trying to reduce it or abstract it into these very basic components that we can then codify as modules in a system. This is really hard, right? It's also not clear whether or not this is actually what we want to create, right? Are these the cyborgs that we're intending to create, or are we actually just inadvertently mimicking parts of ourselves that we either just understand enough to be able to write code about it, or maybe sometimes don't understand the full implications of? It also means that it's really hard to then think about how people are also going to reintegrate technologies into their own worlds. This is an example of a guy who is wearing the Apple Vision Pro spatial computing system while driving, in this particular case, a very prototype version of a self-driving car. And it's tough to watch. He gets arrested at the end, and it's because he is literally playing with an experimental technology in a very real world context, right? There are real cars, real people all around him where we have not yet come to agreement on exactly what it means to create a self-driving car with rules that are respectful of each other and the world around us. At the same time, there are a lot of really inspirational examples, including from the biomechatronics world, where people look at how to actually create human-centered prosthetics that represent and reflect what people want from their bodily augmentations. In so many ways, we are trying to think about what it means to not just create artificial intelligence, but also these artificial bodies. And so I think, again, it is really important for us to sit down and think about the design constraints, the design implications of how and why we decide to design systems in this particular manner, right? If we're creating a control system, if we're creating a control loop, then what are the rules that will govern when and where the loop starts and stops? So from here, we have two directions that we can go in next. You can either continue down the path of looking at each of the different genres of AI, and I believe the next one is on symbolic AI, or you could detour and go look at the section in Module 3 that specifically looks at human-robot interaction and design and the implications for human factors, social context, and global drivers and